did a live stream, so I thought I'd jump in and do a little bit of math. One thing I like to do is, of course, start searching for all kinds of problems to work on. Well, today is no different. I've searched the web looking for some fun problems, and you know, not too surprisingly, a lot of people actually post their test online these days. One thing that they don't post is sometimes the answer key or how to go through those exams. So I found an exam. If you want to do the exam yourself, you'll find a link in the description. I'm going to just start going through the problems and see how they turn out. Fun fact, I have seen these questions sort of, like I had to put them into a nice little PDF so I could actually write on the documents. But other than that, I don't know much about these problems, so I'm kind of going in blind as to what they're about in terms of calculus. But I think that's a good thing. I'll try and narrate as much as I can what my thought process is. That way you get an insight actually how to do these problems. So again, if you want to try this test along with me, go ahead and check out the link in the description. Print it off, try it for yourself. Otherwise, sit back and we'll try a few of these problems. Let's see how many we can do. All right, so let's see, what do we got? What is our first problem on the exam? It looks like this first one, we're dealing with a graph. What do we want to know about this graph? So the graph is a function of f defined from negative infinity all the way up to infinity, and it's given by the following figure. So a lot of stuff is going on there. It's a piecewise function. It's got asymptotes, lines, holes, you name it. I'm guessing that they're going to want to know a lot about limits. Starting off with part A, let me grab my pen here. Part A, determine the range of f. Use interval notation to write your answer. So of course, if we're doing something like looking at the range of a function, I'm thinking about the y values, the output. It looks like there's no way it actually gets above a certain value, so it's kind of capped up there at what looks like 5. But it does have a portion that goes down to negative infinity. So if I want to describe the range, I want to describe all of the outputs that this function could have. So I'm going to say that it goes from negative infinity, and then it goes all the way up to 5. Now again, I'm kind of looking at that dotted line right at 5 to see if it actually gets to that line. And it looks like it has an asymptote off to the right where it kind of curves, and then it has a hole kind of like at the little peak right there. So it doesn't actually reach 5, and I want to use a parentheses on both sides to really indicate that, yeah, it doesn't get to that actual value. Okay, looks pretty good. Let's go on to the next one. Let's see what this one says. So this one says determine the value or write if it does not exist. So it's actually looking for specific function values. We can tell that because there's no limit actually associated with these. It just really has like f of 5 and f of negative 3, in which case we really just have to look at the graph. Let's start off with f of 5. F of 5 actually has two values. You'll see that it has a hole right along the x-axis, but then it has a solid circle right at negative 4. So that's the answer we're going to put for this one, because that is the location, the actual value for the function at that x value. When x equals 5, f of x, f equals 4. Let's see, what's happening at negative 3? Negative 3, we have this dotted line that goes up and down. That's probably because of the asymptote on the left. But it does approach the value of 0. In fact, we see another solid circle at 0. So that's the value we're going to put there. Awesome. All right, continue on. They want us to write an expression for just the piece that goes between negative 3 and all the way up to 2. Okay, so I'm looking at this function here. Let me get a good look at it. The piece that goes from negative 3 all the way up to 2 looks like just a nice line. So really they're tasking us with describing that line. The y-intercept looks like it's at 3. And it has a slope of 1. I know this because it starts at negative 3 there, and if it's going to go through 3 on the y-axis, then it must go up 1, over 1, up 1, over 1. The slope has to be 1. So yeah, we can describe that. It has a slope of 1, so I'll say 1x, y-intercept of 3, 3, and that'd be the line piece of this function, just right there. Okay, not too bad. Let's continue on. Oh, there's those limits that I thought it'd throw in there eventually. Yeah, what limits do we have here? The first limit says, what is happening as x approaches 2? Now, the thing I notice about this one is there's no indication about which side of 2 we're approaching. So we want to think of really approaching both sides. Looking at the graph, if I'm looking at the value of x equals 2, I can see on both sides we're approaching the value of 5. So we'll go ahead and put that in there. All right, next one. What happens as we're going towards positive infinity? I would be this one where we're going towards negative infinity. And I'm seeing this like asymptote. It also goes towards the value of 5. All right, now up to as x approaches infinity. This one approaches an asymptote. It's kind of swooping down and to the right. So this one goes towards -4. All right, time for number 4. It looks like we finally get to 1 where it indicates that we're going to approach only from one side. So this is approaching -3, and that little negative sign in the top says we're approaching from the left side. Okay, so -3 from the left side looks like it's going down towards negative infinity. All right, so negative infinity. Next one. What is happening as it approaches -3 from the right side? That's the one where it's going towards that solid circle at 0. So yep, we'll go ahead that it's also going towards 0. And one more of these. What is happening as it approaches the value of 5? Now this one especially, it doesn't have any indication of whether we're approaching on the right or the left of 5. So we have to think of it as really approaching on both sides. And unfortunately, as I look at this, on the right side it's approaching 0, but on the left side it's approaching -4. So the left and right side just aren't agreeing, which means this is the only one we're going to write does not exist, or DNE. Okay, that looks pretty good. I think that is pretty much it for that page. Let's move on to the next one. Looks like we have a few more questions that also deal with the same graph. What else do we got? This one says determine the largest intervals of continuity for f and use interval notation to describe your answer. So when it comes to continuity, I'm really thinking of like breaks or gaps in the function. Really any place where the limit does not equal the actual value of the function. So we've got a few different places where that's going to happen. It is not continuous at -3, it is not continuous at 2, and it is not continuous at 5. So I'm simply going to write all of the intervals that do not include those places of discontinuity. So we could go from negative infinity all the way up to -3. We could go from -3 all the way up to 2. And we could go from 2 all the way up to 5. I think we have one more. Yep, we have after that 5 to infinity. Let's make sure we got our little union symbols in beneath all of those. So all of these would be our intervals of continuity. Another multiple choice one. What do we got here? Find a number a for which of the following statements is true. So the function f is defined at a, and the limit as x approaches a exists, but f is not continuous at a. So we're trying to figure out some very special properties of this. One, where does the limit actually exist? But for some reason the function is also defined, but it's not continuous. I'm not really sure what it's getting at there. Let's take these one at a time. Let's start off with 0. Okay, when a equals 0, is the function defined there? Yes, it is, because it goes towards 3. Does the limit exist there? Yes, it does. The limit is also 3. Is it continuous there? It happens to be continuous there. There are no breaks or gaps there. No problems whatsoever. So yeah, that's not our value that we really want to worry about. What's our next option here? -4? -4, also no problems. There's no breaks or gaps there. 2, this is what it's getting at. Okay, so 2 is the one that it's really after here. But of course, let's explain what's going on. So if I'm looking at x equals 2, the value of the function exists there. It's equal to 0. That's where the solid circle is. The limit also exists there, but the limit's in a different spot. The limit goes to 5. So the reason why it's not continuous is because those two things are different. The value of the function and the limit are two different things, hence not continuous. We have any other values? What else we got? 5, the limit doesn't exist, so we don't want to look at that one. -3, the limit doesn't exist there, so we won't worry about that one. And the last option says such a number does not exist. That's not true. We found that 2 was really the number where the function had a value and the limit did exist, but since they weren't the same, they weren't continuous. Okay. All right, moving on. Let's see what this one says. So find a number a for which of the following statements is true. So we want one where the function is defined at a, so it has to have some sort of value, and the limit as it approaches from the left side equals the value, but again, it's not continuous. So we got a lot of options to go through. We'll take these one at a time. Starting at 0. So at 0, it happens to be continuous. Not that one. Not going to worry about it. At -4, it's also continuous there, so don't worry about that one. What's it doing at 2? So at 2, the value of the function is defined there. Yep, so we can see that. The limit from the left side equals the function value. No, it doesn't. So I'm not going to worry about that one. What about 5? So 5, the value is equal there. From the left side, the limit equals the value. That is true. And it is not continuous. So yeah, that's the one we're looking for in this case. Last one, a equals -3. No, the function is simply not continuous there. The value is equal to -3, but the limit from the left side doesn't equal the function value. So nope, not that one. Cross that one out. Okay. All right, that takes care of that one. On to the next page. Oh, and looks like we get a new problem entirely. This one deals with a table. Let's see if I can get the table up on my little window here. There we are. We can kind of see it. Maybe I'll resize it a little bit so it looks a little bit better. Excellent. Okay. So what are we doing with this table then? So this table is really giving us information about two functions, f and g. And we're told that it is continuous on the interval that goes from -4 to 4. So we're finding some values of the function using this table. Oh, hey, how's it going? Thanks for joining the stream. If you're just dropping in, yeah, just doing some math problems from a test I found. Yeah, it's actually live, so if you want to ask questions or interrupt, by all means do so. I'm just hanging out, and strangely enough, you know, some people in their free time do hobbies or whatnot. I guess this is kind of my hobby, as I sit down and do math problems. Go figure. Anyway, yeah, let's see, what are we doing with this one? Oh yeah, we're trying to figure out certain values. For this first one, we're looking at f of g of 2. Ooh, that would be a composition of functions. And when we see a composition of functions, we're really thinking of like feeding things into almost like a daisy chain of functions, trying to figure out what they actually end up at. So for this one, we're going to put 2 into g. We're going to get a value. That one's going to go into f. We're going to get a value, and then we'll actually just write the output. All right, let's look at this table. What happens if I put 2 into g? So I'm looking at 2 in the column. I'm looking at g in the row there. Looks like the output would be 1. Let's just write that here. So if I put 2 into g, I get a 1. Right? What happens if I put 1 into f? So I'm looking at that column, I'm looking at f as the row. It looks like I get a value of 4. So that goes in f, and I get a value of 4. So that would be the value of this one, just 4. Okay, the next one involves a limit. One is dealing with a composition. One is dealing with a multiplication, I guess. Now, it tells me that the functions are continuous on the -4 to 4 interval. So even though we're dealing with a limit, because it is continuous, we can really just plug in the value of where that limit's going towards. It's going to be the same as just evaluating it there. And again, we really get that because it is continuous. So let's do that. Let's see, what am I looking for here? F of 0, g of 0, minus f of g of 0. That's really how we want to think of this one. Okay, f of 0. What is f of 0? That one looks like it's a 5. G of 0 looks like that goes towards a -2. Okay. Now I want to think of putting 0 into g. So that gives us a -2. -2 goes into f. That gives us a -4. So we have -4. Okay. So this one requires, just a little bit of cleanup, but, it's actually not too bad. 5 times -2, that's a -10. Minus a minus would be a +4. So combining those things, we get a -6. And that would be our answer for that one. Okay, not too bad. Let's see, what else we got? Moving on. This one also says to use the table. Let's see, can I scroll down? Oh, there we are. So use the table above to find the following limit. First, write the form of the limit. Right does not exist only if the limit does not exist and it is not positive or negative infinity. Show your work, justify your answer, all that good stuff. Okay, so let me think, what is it really trying to get at here? So it looks like it's kind of getting almost what you would see for like a derivative, but not, because I got that g of 3 plus h minus 4 thing on the top. And I guess it's trying to, well, let's see, we don't have a derivative. And we can't, well, let's see, can we plug in 0 directly? We'd get a 0 on the bottom, so I guess that doesn't necessarily help. What is this? What's this problem really getting at? Use the table above to find the limit. First, write the form of the limit. Right does not, okay, so first we have to write the form of this limit. So I guess that would be more indicating of what the derivative is. Maybe that's what it's trying to indicate at. Okay. Okay, so we're thinking about 0, and we're thinking about how maybe the function changes there. Almost like a right-sided derivative. Almost. You know, I just don't understand the instructions, what it means by write the form of the limit. Because it looks like we already have a limit, so I guess I'm just going to have to skip that one. Maybe I'll come back to it and figure out what exactly it's talking about. But yeah, that one, I'm not really sure what it means, write the form of the limit. Oh well. Let's see, what do we got for this next one? Part C. This one says, circle the correct answer. The intermediate value theorem implies that the equation f of x equals 0 has a solution on the interval. So let's see, f of x equals 0. Oh, okay, so we know that f is a continuous function, and we have various different values in our table for f. So the question is, you know, where would we expect the intermediate value theorem to guarantee that we actually have a 0? And where we'd have a guarantee of having a 0 is where it changes sign. So notice in the table, that first row there, f goes from -4, and then it goes to +2. Since f is continuous, the intermediate value theorem tells us that it has to have a 0 in that interval. That goes from -2 to -1. So let's go ahead and look at our options. I bet that's got to be one of them. And sure enough, there it is. It's right there. So that's where the intermediate value theorem would apply, and where it would tell us it has to have a solution. Perfect. All right, I got a little bookmark that we're going to come back to that one eventually. Let's go ahead and on to the next page. All right, so this one, it doesn't look like there's anything to look in terms of a graph, so let's get that off there. And this one looks like it is talking about the intermediate value theorem in general. This one says, explain how the IVT can be used to show that the equation, x sine of pi over 6x is equal to 1, explain how that has a solution on the interval that goes from 0 to 2. Make sure that the conditions of the IVT are satisfied before you apply the theorem. Sounds like a great idea to me. Let's go ahead and do that. So if we're going to apply the IVT, there are really 3 things we have to mention. One, we want to mention that the function is continuous. And actually, looking at this, we don't have a function yet. We better build a function. So let's do a little prep work. I'm going to say let f of x equals, and then I'm really going to take the equation and just move everything over to one side. So x times sine of pi over 6x minus 1 equals 0. So yep, we're turning it into this guy right here. Perfect. So that's going to be the function that we actually apply the intermediate value theorem on. Right, now we get into those 3 bullet points. One, we want to say that f is continuous. And this one happens to be continuous everywhere, but if it wasn't, we'd specifically mention that it's continuous on the interval that goes from 0 to 1. Oh, that looks like we got someone else. Is it a replay? No, this is not a replay. I'm actually here, though. If you see this in the future, like sometime after February 28th, then it will be a replay. Anyway, let's see what we got here. Let's see. It is continuous. Oh, how do I know it's continuous? Because it is made of continuous functions. Since x is continuous, sine is continuous, and the number 1 is continuous, and the product and sum of continuous functions also happens to be continuous. Okay, so I have a really brief explanation here, but let's see if I can kind of read it out, or at least read what I'm thinking. So it says f is continuous, and the reason why I know that is because the function x is continuous, sine is continuous, the number 1 is continuous. All of those are continuous functions, and really we're just either multiplying or subtracting or adding them. And when you multiply and add continuous functions, you get another continuous function. All right, so that's the first bullet point. What else do we want to show for this? Well, the next thing we really want to show is that we have some value less than 0 and another value greater than 0 on the interval. Now I'm guessing if they gave us the interval was from 0 to 2, those are probably usually a great first place to start searching for values. So let's plug in 0. Let's see what we get. All right, so plugging in 0, what does that go to? Well, 0 times sine will give us 0. Subtract 1, and we get negative 1. So this is negative. Right, now let's plug in the value of 2. So 2 times sine of pi over 6 times 2 minus 1. Ooh, so we got to do a little bit of evaluating there. 2 pi divided by 6, that's just pi over 3. And now we actually have to figure out what is the value of sine of pi over 3. So we need our, what is it, our unit circle. It looks like I get a value of square root of 3 over 2. So equals 2 times the square root of 3 over 2 minus 1. Square root of 3 minus 1. So I don't know actually what number that is off the top of my head, but I do know that it is some sort of positive number. And really that's all we need for this particular theorem, is we need a positive number and we need a negative number. So we know the function is continuous. We have a negative number on one side of the interval. We have a positive number on the other side of the interval. Those are the 3 ingredients we need. So now we can say by the intermediate value theorem, f has a 0 in the interval that goes from 0 to 2. Hence the equation, hence the equation that we're even working with at the very beginning has a solution. And that would take care of that one. Nice. Yeah, that one involves a lot of work. Thoughts or questions? Yeah, I didn't see any more parts to this one, so I think that one's good. All right, let's move on. I think, you know, this entire test, they give you like 55 minutes to do. I don't know how long it's taken me so far, but I think, you know, I think we're moving at a pretty good pace. So let's see, page 5. This one says, write the form of the limit where indicated and evaluate the limit where it does not exist, only if the limit does not exist, positive or negative infinity, justify your answer. Okay, so maybe there's like a table or something associated with g. What is g? Oh, yes, it looks like g is a piecewise function. Let me see if I can pull it up on my little window here so we can see it as well. There we are. Maybe like There, that worked. Okay. So g is a piecewise function, and we're supposed to figure out stuff like various different limits. Okay, so I'm guessing when it says the form of the derivative, we actually want to write the piece of the function that we're actually looking at for the limit. We can do that. All right, so let's do the first one. So the first one says, find the limit as x approaches 1 from the left side. And looking at the piecewise function, 1 is bigger than 0, so I'd be using the second piece to this piecewise function. So I'm just going to write that here. I know it says, well, it says write the form, but I don't want it to get in the way of where I'm at. So I'm going to write the limit as x approaches 1 from the left side, and we'll do 1 plus the square root of x over 1 minus the square root of x. Okay. Now, if I was to plug 1 into the top and bottom, it unfortunately gives me a 0 in the denominator. The top, it really just goes to 2. So if you want to think of this as the form that it turns into, the form is like 2 over 0. Now, that immediately tells me that it's going to go towards positive or negative infinity, depending on what sign it is. So yeah, let's see. Does this go towards positive or negative infinity? Well, on the top, I'm not really worried. That's going to go to a positive 2. But on the bottom, since I'm just a little bit less than 1, I'm on the left side of it. That means when I do 1 minus the square root of something just a little bit less than 1, I will get some sort of positive number. So something like that. So I know that this will go towards positive infinity. All right. Let's see, what else do we have here? Looks like we have the limit as x goes towards negative infinity of g. Okay, yeah, we can do that. Let's get that one up here. So this one is definitely less than 0. So if I'm thinking about the pieces that I'm looking at the limit as x goes to negative infinity, and we're using that e to the x piece. So for this one, what's going off in my mind is really the shape of the graph of e to the x. It has that nice exponential curve to it, which means this thing is headed towards 0. All right, not too bad. Moving on, let's see what else we got. The limit as g of g as x approaches positive infinity. Okay. So this is kind of like the last one. I'm looking at the limit as x approaches positive infinity. And now the two pieces I have here are the square root of x all over 1 minus the square root of x. Okay, that looks good. So yeah, what do we got going on here? So it's approaching positive infinity. I could really think of the two parts of this that have the biggest effect. In other words, the pieces that actually have x in it. Those are the ones that are really in the driver's seat. So square root of x over negative square root of x. Now, both of these are the same. So one is going to be positive and the other one is going to be negative, just from, the signs being out front. So I know that this will actually go towards negative 1. And that'd be the value of this limit. All right, looks like that was the last one for this page. Onward we go to page number 6. Oh, looks like are we still dealing with the same function? I think so. Yeah, now we're just looking for various different asymptotes of our function. Starting off with any vertical asymptotes. Does it have any? Does it not have any? Whatnot. Well, I think we already found from an earlier part that it does have an asymptote. When we were doing part I, and we were approaching 1 from the left side, we saw that it went to positive infinity. So that's going to be one of our vertical asymptotes. So I'm just going to write x equals 1. Let's see, are there any other vertical asymptotes in there? Well, that'd really only happen if the denominator of one of these functions would give us a 0, and that's the only place that's going to have anything that does that. E to the x is always going to be e to the x. That's a nice continuous function. There's no asymptotes in that, so it's not going to produce any of those. What about horizontal asymptotes? That's the next part. Does this have any horizontal asymptotes? Well, yeah, we actually found a couple of those. scoot that up just a bit. One of the horizontal asymptotes we found came from that e to the x. As we were heading towards negative infinity, the entire function went towards 0. Now we also got another one as we're heading towards positive infinity. This one's actually just going to go towards negative 1. So this one happens to have two horizontal asymptotes. Sometimes that happens. All right, moving on. What does this one say? It says, use the definition of continuity to determine whether the function g is continuous at 0, and then show your work. Okay. So what's going on at 0 specifically? If it is less than 0, we get e to the x. If it's greater than 0, it's equal to this other thing. Okay. So in order for this to be continuous, you really have to check three things. One, what's the value of the function at 0? And then what's the left-hand limit and what's the right-hand limit? Those are really the three things that have to match up. If any one of those is not equal to the other ones, then it's simply not continuous there. So yeah, let's check what's going on at 0. So what is g of 0? What is that value? Well, when I plug in 0, it says we should use this e to the x piece. E to the 0 is just 1. So that'd be the value of the function. Now the limit from the left side of 0 also uses that e to the x piece. So automatically we know from the left side it's going to equal the same value of 1. So the only thing that I'm really interested in is what happens as it approaches 0 from the right side. Limit as x approaches 0 from the right side. This will use the 1 plus the square root of x all over 1 minus square root of x. Okay, if I just plug in 0, neither the top nor the bottom go towards 0. So I really can just look at really just plugging it in directly, and sure enough we get 1. So those are the three things. We check the value, we check the left-hand limit, the right-hand limit. They all equal the same thing. So we can say that yes, this is continuous. Very nice. All right, moving on. What else we got? The last one, it says determine the intervals of continuity for g and use interval notation to describe those intervals. Well, I think we've already done a lot of the work to really describe where it is continuous. Starting off with that e to the x function, it is going to be continuous everywhere on its domain. So we've determined that, if I start way back at negative infinity and I go up to 0, it's definitely going to be continuous there. Part D, we've also determined that it is still continuous at 0 as it makes the transition into the other function. Where it is not continuous is really at that value of 1 because it has that vertical asymptote. So these intervals would really describe where the piecewise function is continuous. All right, very nice. I think that's the end of this page. We're moving right along. On to the next page, page 7. Let's see, do we need any... I don't think this is associated with any graph or anything. Nope. So I'm going to take this off of here so we can actually see what we're doing. Yeah, let's read the problem. This one says, write the form of the limit and evaluate each limit. So write that it does not exist only if it doesn't exist and it is not positive or negative infinity. So these are just kind of straight up just like evaluate the limit. What do you get? All right, so let's see what's going on with this one. This one, we are approaching 3 from the left side. Sounds good to me. Step number 1, anytime I'm trying to do a limit, I'm just going to plug it in. I just want to see if that actually equals something. So 3 minus 5 squared minus 4, all divided by 3 minus 3. So let's see, up top we'd get a, looks like a negative 2 squared. So that'd be a 4 minus 4. And sure enough, looks like the entire thing just gives us 0 over 0. Now, unfortunately, that doesn't really give us any information. It means that we probably have to do some manipulations to this, or be a little bit more careful of how we're approaching 3 from one side or the other. Okay, we'll do that. Alternate options, if we had our derivative rule, we could use L'Hopital's rule. Unfortunately, looks like they're anticipating that. They say, do not use L'Hopital's rule. Show your work in some other way. So fine, definitely not using that. We'll just try and use maybe some algebraic manipulating as best we can. I wonder, part of me wonders if this thing will factor. So let's go ahead and play around with the top a little bit. X squared minus a 10x plus a 25 minus 4. So if that minus 4 is on there, then I guess we'd get a 21 on the end. Let's see, what two numbers would give us a 21? I think that's 3 and 7. We want, let's see, both of them to be negative, because that's how we would get the 21. Negative 3 times negative 7 would give us the positive 21. Negative 7 plus a negative 3 would give us the negative 10. So yeah, that's our middle term. Okay. All right, so that's what's happening with the top. It actually does factor. That's cool. And now we can be a little bit more careful of what's happening with the bottom. So we're approaching 3 from the left side. We have something just slightly smaller than 3. What that tells me is that this expression that we get in the bottom, it's actually going to be a negative quantity. So I don't, these absolute values are there. I want the absolute values to take that negative quantity and make it positive. An alternate way that we can do the behavior of an absolute value and still get a positive quantity is, if we know something's negative, is just to multiply it by another negative sign. And we know this is going to be negative, so I'll just multiply it by a negative. That will have the behavior we need. Okay, this actually looks good. This is really good news. I can see we have a common factor of an x minus 3. We're going to cancel those out. And now I'm just going to look at the limit as x approaches 3 from the left side of x minus 7 all over negative 1. Okay, that's much, much better to look at. Yeah, now we can just, plug it in directly and see what we get. Yeah, what is 3 minus 7? That'd be a negative 4 over negative 1. Oops. So overall, looks like this just goes to a positive 4. And that'd be the value of this limit. Nice. Yeah, anytime you have 0 over 0 and you don't have the option of using L'Hopital's rule, it really just comes down to doing a little bit of algebraic manipulations and seeing if you can eliminate the problem area. And that's what we did. We factored it and got rid of the extra term of x minus 3. All right, on to the next one. What do we have for this one? The limit as x approaches 1 of x over x plus 5 minus 1 over 6, and then all over x minus 1. I'm guessing this will also be a 0 over 0. But let's go ahead and plug it in and see what's going on here. So 1 plus 5 minus 1 6. Yep, the top's definitely going to go to 0. We got 1 6 minus 1 6. And sure enough, in the bottom, there's a 1 over 1. I'm thinking maybe that's the form that it really wants us to put over here. So it wants us to put that this is the form 0 over 0, and maybe justify why we're doing some of these algebraic steps. Sounds good to me. All right, so let's see what we got here. So this contains a bunch of fractions. One way that we can potentially get rid of that problem area of x minus 1 is to get rid of those extra fractions. In other words, try and combine those. So let's focus on the top for just a little bit. I'm going to multiply the top and bottom by 6. Really, that's giving me a common denominator for that fraction. The other one, I'm going to multiply the top and bottom by an x plus 5. Okay, that looks pretty good. I could go ahead and combine the numerators. So 6x minus 1x, that'd be a 5x plus 5 all over. So 6x plus 5. And all of that is really just in the top. If we wanted to, we could even factor this further. We can take out that common 5. So really, that's what's happening in the numerator. Okay, so we have that. Set that off to the side. And this is being divided by an x plus 5. So we're going to put a little x minus 1 in the bottom like we have there. Let's see, is there anything else that we're missing? The top, I thought it went to 0 over 0. Am I missing a sign in there somewhere? Oh, sure enough, we are. Yep, I didn't distribute my sign. So we should subtract the x. We should subtract the 5. Let's go ahead and make that fix. So that's a minus sign, that's a minus sign. What tipped me off is it didn't cancel like it should. It was indicating that there was no problem in the first place, and we saw that there was a problem. Oh, hey, Chill Breeze, how's it going? Just saw you enter the chat. Just sitting down and doing some math problems. Almost done with this entire set, so in a moment we'll probably just sit down and chat and maybe answer other questions you have. All right, let's cancel these guys out. Now that the problem area is eliminated, now we'll go ahead and take the limit. You know, once you really eliminate that problem area, there's not much left with taking the limit. It really is now just a matter of plugging it in. So let's see, we get 5 over 6. If I plug in the 1, we'll have another 6. So this really just reduces to 5 over 36. Oh, I got messed up in my little message on the bottom there. Let's see, maybe I can scoot over just a little bit. 5 over 36. Yep, I think we can fit it in right there. Perfect. All right, so let's see. That is page 7. Scooting right along. One more. Page number 8. What do we got? Oh, we got one more limit left. Let's see. What do we got for this one? This is the limit as x approaches negative infinity of the square root of 3x squared minus 3 plus 2. And that's all that's divided by an x minus 2. Interesting. So let's see. How are we thinking of this one? If it's approaching negative infinity, the top is essentially getting bigger and bigger and bigger. The same thing's happening really with the bottom, but it's a negative number. So it's asking for a form. I would describe this form as infinity over another version of infinity. Technically negative infinity on the bottom, but some version of infinity. So essentially we just want to be very, very careful of the signs that are present in here to see if this gets close to a specific value. All right, let's see. What shall we do with this thing? Maybe what I'll do is I'll take the largest terms present and really just focus on those. So the largest power of x in the numerator is underneath that square root, is 3x squared, and the largest power in the bottom is just the x squared. Now I'm going to maybe try and cancel some stuff out and see what happens there. So I'll still have the square root of 3. If I take the square root of something squared, then I'm dealing with the absolute value of x. So I have this absolute value of x in the top and I have an x in the bottom. X is approaching a negative infinity. So really we're thinking of it as a negative quantity. So I have a positive number up top. We have a negative number in the bottom. So those are canceling each other out, but they're canceling out and giving us a negative 1. So the value of this last limit that we're really dealing with is a negative 3. Cool. All right, I think we've done pretty much all of the problems in here, but there was a limit earlier that I think we ended up skipping. Let's see if we can find that. Was that around page 2? Nope, I don't see it there. Maybe it was page 3. Yeah, there it is. Okay, this is one where we're looking at some sort of function for g. And we had to determine the form of the limit and then eventually just figure out what the limit was. Oh, okay. Let's get the function back up here. There it is. Because now, after doing those other problems, now I have a better sense of what the quote-unquote form is that it's even looking for. So this one, what it wants to do is really just, describe it. Is this a type 0 over 0, infinity over infinity, like what's happening? All right. Using our, did this actually come from a table? This came from a table. I don't want the piecewise function. I want the table. There's our table. All right. So if I was to plug in 0, then I'm essentially just looking at g of 3 for that little first part there. And g of 3 goes to the value of, what is that, 2? So if I plug in a 3, that should go towards 2. So up top I have 2 minus 4. Meanwhile, the bottom's going towards 0. So I get like negative 2 over 0. So that tells me that what's happening with this one is the value of it is going towards positive or negative infinity. It really just amounts to what sign this is going towards. You can see that the top of this is going towards a negative 2. The bottom, since we're approaching 0 from the right side, is going to a positive quantity. So overall, this will go towards a negative infinity. There we are. And that would really be our last problem. Oh, hello, welcome to the chat. Just sitting down and doing a few math problems. And as you would know it, we just did the very last one, which I guess is kind of good. It means if you have other questions, we're just going to sit down and chat and see what other things you might have. Probably got about, I don't know, 20 minutes or so. Just got some time to kill. So if you do have questions, feel free to drop them in the chat box. I'm going to get a blank page so that if you do have questions, we can go ahead and check it out. Perfect. Oh, and I guess we don't need that anymore, so let's take that off. So yeah, how's it going? What's everyone up to? I hear that in a lot of schools it's getting really close to midterm season. Any interesting problems you've come across? I'll say one interesting thing that I've come across is, I'm always suggested various different math things. And one thing that has just fascinated me is someone has been developing a graphics engine in Desmos, which blows my mind, to be quite honest. Something like a graphing program or a graphing calculator has just enough functionality in it that it seems perfectly reasonable that you could do something like that. But all the work that it would take to actually put it in there is just mind-boggling. After watching some of their videos, you can tell where it's not the best medium for it. It takes quite a bit of time to do a lot of the number crunching and actually have it produce some good images. But again, just the proof of concept, the fact that you can do it is just mind-blowing. It's amazing. Interesting. Yeah, yep, just sitting down doing some problems. If you like the music, also check out the description. There's links to the music, so if you enjoy them, you can find out who the artists are and, of course, support them as best you can. Oh, speaking of links, you may have noticed that I haven't posted a whole lot in probably the past few months. Though the good news is that doesn't mean that I haven't been busy. In fact, you can probably just tell by this little space here that I've been very busy kind of like perfecting my craft and getting really a little bit better at producing some much nicer videos. And part of that is because I've partnered with a company called Wise. So they also do like educational videos. They do a variety of them in like math and the sciences, biology, chemistry. So if you're interested in checking them out, definitely check out the link in the description. I have a code down there where if you decide to use it, you can get 10% off a subscription at Wise and get access to some really great courses and instructors. One of the big reasons why I decided to partner with a company like Wise is because I really like the other instructors and I like how they also have the same mission that I do. We really just want to help people learn and do it in the best painless way possible. Oh, hello. This says you want to know. Well, hello, you want to know. Hey, that's really cool. How'd you get the little YouTube emoji in there? Can I do that? Oh, no way. I didn't even know that was an option available. good to know. Excellent, excellent. Yeah, that test went by way faster than I thought it was. Let's see, somewhere at the beginning of this, it says that, yeah, this is this test you're permitted to have 55 minutes for. But yeah, if you really know what you're doing with the problems, they can be knocked out fairly quickly. Oh, sounds like you have some very interesting type of problems. So you're doing the volumes using cross sections, shell, washer, average value of a function, trigonometric integration, homework. Sounds crazy. But I'll tell you what, if you got a problem, we'll go ahead and work on it. Those are very good topics, and yeah, I have no problems doing some volume problems. Actually, they're actually kind of fun if you think about it. You know, taking some sort of generic function. I'm just going to draw one here. Here's my function. Rotate it around the x-axis. So maybe we stop it right there. And if we take a two-dimensional like region like this and we decide to rotate it, of course what this gives us is something in 3D. Which means now I get my best practice at trying to draw three-dimensional objects. Here we go. So let's see, it stops at the end there. Things are being rotated so that it stops in kind of like the circular. This one kind of looks like a bell, I guess. And we'll do a little dotted line on the inside. Sounds pretty good. So the slices of this one would just really be a whole bunch of circles. Which brings us to what the integral, the setup for this one is. Since the slices look like circles, that's essentially what we're adding up when it comes to the integral. So the integral goes from a to b, pi. The function is really what's controlling the radius of all of these circles. So I'm just going to write this as f squared. And then we'll have like dx. So this would be the volume using circular slices. Well, good. You know, that's really what this is here for. So if you're just doing your own homework and just kind of like chilling out, that's kind of what I'm doing too. I'm just, you know, doing some math, chilling out, and, you know, gives you some good music to listen to in the meantime. Yeah. If you got a question, go for it. You're more than welcome to ask. I am actually completely live right now. So let's see, if you're watching after February 28th, this is obviously not live, but yeah, it's live right now. Says my bit rate is low. How can I is there a way that I can improve my bit rate? It says I can. I wonder if I can just bump this up. Ultra fast. Let's see if that works. You also mentioned finding the volume using the cylindrical shell method. So, yeah, that's also another good one. Let's see if I can draw my best picture for those. So we still have a function, something like that. So that would be the region. There's our f. If we're doing cylindrical shells, this is rotating usually around the opposite axes, you know. So if my function is defined in terms of x, then I'm really rotating this around the y-axis. So now let's see if I can do my best three-dimensional shape here. So on the bottom of this, that's where we're going to get the circles. There we see the profile of the function. And these circles really kind of emanate out from there. It's like got a divot. It almost looks like a cylinder, but because of the function, it's got like this funnel shape to it. All right, not too bad. Yeah, what would the formula for this one look like? Well, it would use the formula for the volume of a cylinder. So we're going from A to B. The volume of a cylinder, what is that? Pi r squared times the height. So pi. The radius in this case is being controlled by your value of x, so pi r squared. And the height is actually being taken care of by the function, pi r squared. So pi r squared multiplied by the height, dx. Oops, not dy. Why do I do that? Dx. There we go. So let's label this one. This is the volume of cylinder. That's okay. I know there is a little bit of a delay when you do live streams like this. All right, looks like the settings I did in my little OBS actually worked out. It says the stream is now healthy. That's good to see. Oh, let's see. I think, yeah, I made a mistake with my formula here. I don't want pi r squared. What am I doing? I'm thinking of just the volume of a cylinder, but I want the shells themselves, the volumes of the shells. And the shells are cylinders, but if you unfurl them, they turn into basically rectangles. Oh, we need to make some adjustments. This is wrong. I don't like this. Because, yeah, we take an individual shell and we flatten it out. There we are. And that's important because the two quantities that we're really keeping track of here are the circumference of that shell and the height of that shell. That's what we want to keep track of. So this is 2 pi. The radius is being taken care of by x. and then the height is being taken care of by our function. The thickness of the slice is actually being taken care of by the dx on the end. There we are. Shell. I think I am running out of room on this one. I will have to probably erase some of this, but that's okay. See, how many people do we have here today? All right, looks like we got a couple. Great to see you there. Great to have you. An algebra question, huh? Okay, okay. If it's an algebra question, I'll go get my algebra template. Here we are, algebra. Cool. All right, let's go ahead and just write that down. If 3x minus y is equal to 12, excellent. So this one looks like you're just really kind of playing around with expressions, kind of getting a feel of doing some substitution, and maybe even simplifying or reducing an expression as best you can. The reason why I say that is, you know, we're given one equation, 3x minus y is equal to 12, but you're not given a second equation, so we won't actually be able to get a number for both x and y. Oh, okay, so it's 8 to the power of x and 2 to the power of y. Okay, we'll make some adjustments. Excellent. So yeah, we don't know what either of those are, but we will be able to, let's say, find an expression for y, and then do some substituting from there. Okay. Let's start off with the initial expression here. So this is 3x minus y is equal to 12. And what I'm going to do with this one is I'm going to solve it for y. My goal with this one is if I can solve it for y and end up substituting it into this y here, then we'll be able to reduce this fraction, since the only variables we'll have in there are really x's. All right, so how can we solve for y? I'm going to add it to both sides. Then I'm going to move the 12 to the left side. Okay, so this really just gives me an expression for y. Sub it in. Let's see, what does that give us for our expression? So now we'll have 8 to the power of x, all divided by 2 to the power of 3x minus 12. right? That's a little bit closer to what we actually want in terms of being able to reduce this. In order to use our laws of exponents, we really want the bases to be the same. And we're almost there. You can see that the bottom has a base of 8, and the top has a base of 8, and the bottom has a base of 2. So we can rewrite 8 so that it also has a base of 2, since 8 is the same as 2 cubed. Let's do that. So this is 2 cubed, and that's multiplied by an x, so that would be your 8 to the power of x. All of that is being divided by 2, 3x minus 12. All right, now we can go ahead and apply our rules for exponents. So I'm going to take the top expression here, and I'm going to subtract the bottom power, so 3x minus 12. Note that I'm using parentheses in here because I want to make sure the entire bottom power is being subtracted. If you forget those parentheses, you will end up with a small sign error. So 2 to the 3x minus 3x plus 12. Hey, how about that? Looks like the 3x and the 3x actually cancel out entirely. So we're left with 2 to the power of 12. And hey, now we don't have any more variables in there. We actually have a number. 2 to the power of 12 is actually not too big. Looks like this one equals 4096, and that'd be it. Does that help out with that one, or do you have other questions about how to do that? Excellent, good to hear. You know, the fun part about having a problem like this is sometimes there's more than one way that you can approach it. You mentioned that you're going to rewatch this and maybe see how we solved it in this way. I'm going to have some fun with it. Let's solve it a different way. In this problem, we solved for y to begin with, but actually there's nothing that says you have to solve for y. Why not solve for x? This will make the problem more difficult, but there's nothing stopping us, so let's do it. So to solve for x, I'm going to add y to both sides. And then let's see, I bet I can divide, no actually that'll probably be just fine right there. Yeah, let's just leave it like that. So again, I'm going to go back over to my problem, and I'm going to rewrite the 8x as a 2 cubed. And if you really want to break it down into steps, so the 8 is becoming a 2 cubed. And then from your rules of exponents, the 3 and the x get multiplied together. So where we're going to sub this in is right there at the top, because I see that it has a 3x, and you know, in working our equation, we also have 3x. All right, so let's replace that. So we have 12, or I have 2 raised to the power of 12 plus y, and in the bottom we have 2 to the y. So we have a slightly different expression here going on, but no worries, we can still use our rules of exponents that says I will take my top exponent minus my bottom exponent. And just as before, the variable is going to drop away entirely, and we're left with 2 to the 12th, which we already said was, what is that, 4096? So there we go. So that's just a second way that we could approach it. And it's really nice when you see something like that. It shows that the math is really consistent. You get to the same answer either way. Good deal. Yeah, if you got a fun exam that you want to send my way, give it a shot. We only have a little bit of time, so I may just end up picking a few problems out of it, but you know, we'll do what we can. All right, looks like we had a different problem. So this one says, why do some textbooks stop showing each step when solving equations? I think part of it is, they kind of assume that, they assume that you're familiar with the solving process at some point and just kind of stop doing it. It's unfortunate, but they're also trying to make sure that the book doesn't get too long. I guess the other part is, they're written by humans, and humans, especially mathematicians, tend to be very lazy. So we'll often do shortcuts or not write as much as we probably should. All right, let's see what this one says. So solve this system of equations. Solve a system of equations. All right, so what do we got? We got 8x minus 5y, and that's equal to a negative 14. And then the second equation is simply y equals a negative 3x. Excellent. So when it comes to solving a system of equations, you actually have a couple of ways that you can approach it. You have the substitution method or the elimination method. In the substitution method, this works really good if you have one of your variables already by itself, which in looking at the system you gave me, it's exactly what we have. The second one is already solved for y. So this is going to make me lean towards using the substitution method. Use the substitution. All right, how does that work then? Well, I'm simply going to take the first equation, and everywhere I see a y, I'm going to put the second equation in there. So we're going to put the negative 3x everywhere we see that y. All right, so that looks a little bit better. Now we really just want to simplify what we can and work on getting the x all by itself. So I still have the 8x. Minus times a minus will be a plus. 5 times 3 will be a 15. And then we can go ahead and combine the 8 and the 15 together. So 8 plus 15, what is that, 23x? Looks pretty good. One last step here, it looks like we would divide both sides by 23. And we have half of our solution. Keep in mind what we really have, for a full solution we need both the x and the y values, so we still have more work to do. But again, that second equation is already solved for y, so we can go ahead and take this value, run it up, and put it in that other equation. So y equals negative 3, and I'm going to substitute the value of x in there. So y is equal to, negative times a negative will give me a positive. So let's see, what is 3 times 14? That's 42. 42 over 23. And there's our second half of our solution. So you really need both the x and the y value. Thank you, that means so much. Yeah, we're just sitting down doing some problems. But looks like I'll only be here for just a few more minutes. Speaking of which, if you want to see any of my other videos or anything like that, let's see, what do I want to say? Oh, I've partnered with a company called Wise Prep to actually put out a full entire course of math videos. So if you want to check out the link in the description, there's actually a discount code if you want to go check them out, and also see some of the other great instructors that I've been able to meet. Of course, I just really stick in the math realm, that's all I really do, but there's some other really great people who do like chemistry and biology, so I definitely recommend you check them out if you're taking some of those other classes. They have courses in high school, university, college, all kinds of them. And of course, I have lots of fun making videos for them as well. So if you want to see even some of the other videos that I've been doing that are kind of off my YouTube page for this company, go check them out. Yeah, that's sometimes the problem with those exams. You know, they already have answers in them. The one that I found didn't have answers in it, so I was able to just kind of, give my own interpretation as we were going through it. Did you send it to my email? I'll go check my email real quick. Nope, that's not it. Well, where did this thing go off to? Oh, okay. Sounds good. Writing the standard form of a line. Looks like we're going to need a little bit of room, so here's what I'm going to do. I'm going to clear all of this out. Let's see, probably just by kind of tossing the whole thing. And then we'll open up a new little whiteboard here, and we'll give it a shot. So this was the algebra one. Perfect. Write the standard form of a line. Okay. Now, when I hear those words, standard form of a line, the template that immediately comes to mind is this. Ax plus by is equal to c. That is the standard form of a line. We want a and b and c. We don't want any fractions on our variables there, and we want the coefficient in front of x to also be positive. So as we're going to take the information that you have and write it in that standard form, those are other things we'll be working into this. We don't want fractions, and we want to make sure that a is a positive number. All right, let's see what we have here. I'm going to write example. We have that our slope is going to be a 2, and that it happens to go through the point 4, 3. It looks like we'll also be graphing that. Sounds like good information. Now, the information that you're given is really kind of geared towards if you have, if you're trying to write the equation of a line. So from this, we can write the point slope form. The point slope form of a line is y minus the y value, slope x minus the x value. That is to say, this will, we can go ahead and plug in our point. So the y value is 3, our slope is 2, and our x value is 4. So this kind of gets our foot in the door in that we at least have the equation of a line. Now from here, it's just a process of getting everything, the variables kind of shuffled over to the left side so that it is in that standard form. So I'm going to distribute through by the 2. It's a 2x minus an 8. And now I'm going to start shuffling things over to the left side. So negative 2x plus y. I'm going to add the 3 to the right side. It's almost in standard form. We don't want that negative sign on the x. So I'll multiply everything by a negative. And now we have our standard form. Okay, the standard form is actually a pretty good form. It's not the most useful for graphing, but it is a good one to write the standard form. All right, let's see what we can do in terms of the graph of it. For the graph, I need a ruler so that my lines actually look straight. Let's see, where did I put that ruler? Oh, there it is. Perfect. So let's see, what do we know? It goes through the point 4, 3. 1, 2, 3, 4. 1, 2, 3. So I know for sure it goes through that point. 4, 3. Now with the slope, I can use it to build another point. So starting at 4, 3, I can go up to over 1, and that will be a second point. So let's get back. So it goes over, up 2, up 1, 2, over 1. Here is a second point. So up 2 over 1, that'd be at 5, 5. And let's see, if I want to go down 2 and to the left 1, that would also give me another point. So down 1, 2 over 1, down 1, 2 over 1. And really, I'm drawing a few points on here just so that my line is fairly accurate when I graph it here. The more points you do this with, the better it looks. So, you know, you get a few on the page, starts looking really nice. Cool. I like it. I like it. Be careful. It kind of looks like it goes through the value of x equals 2, but it doesn't quite go through that value. That is not one of our intercepts. Fun fact, when you have a line that is in standard form, it actually gives you access to what the intercepts are by plugging in a 0 in just the right spot. Check this out. So I'm going to write down the equation in our standard form. Let's make a little note. Find intercepts. If we want to find the intercepts, then what we do is we set either x or y equal to 0, and we solve for the other variable. So when x equals 0, y equals -5. When y is equal to 0, then x is equal to 5/2. So those are the two intercepts, or the two places where it crosses our axes. Well, let's go ahead and mark them. So this one down here on the y-axis, that's the one located at 0, -5. And this one, that's the place where it kind of looks like it's at 2, but it's not quite. That one's actually at 5/2. Cool. All right. Unfortunately, it looks like it's the end of the time that I have today, but don't worry, I'll definitely be doing a lot of live streaming this week. So if you've got some more homework or other problems you want to throw at me, feel free to send them to my email. I'll probably pick them up starting tomorrow, all right? You guys have a wonderful day. This was a lot of fun, and you can guarantee that I'm going to do a lot more live streaming in the future. You guys have a good one.